This lesson will give an introduction to completely randomized designs, also called CRDs. So just to give you kind of an overview, we're going to introduce completely randomized designs by talking about the model and some notation that we'll use for these designs. We'll then give you an idea about the analysis of variance ANOVA table, which again should be a review from Stat 5615, and give you just a little bit of limited theory on ANOVA so that we can discuss this type of model. So one of the examples that we'll use for for the completely randomized design is the highway paint example. The goal of this example is to compare reflectivity measurements of 3 new paints to the current one used on the highway. So they have 16 similar sections of highway, and they selected it so that each type of paint is randomly applied to 4 sections. So again, they have the 3 new paints and the one that's currently used, so they have a total of 4 treatments, and those are going to be randomly applied to the 4 sections. So here the response is going to be the percentage decrease in reflectivity, and they're going to have 1 treatment factor, which is your paint. So we have the 4 levels of that. And we also talked a little bit about just notation and terminology and when we introduced experimental designs in the last lesson. And so again, lowercase n here is going to be 4, our number of replications, and capital N here is the overall sample size. So since we have what's called a balanced design, we see every treatment the same number of times. We have a total of 16 experimental units. So again, with a completely randomized design, you'll notice that we have a treatment factor here, and we're looking at a response, a measurement here, and this reflectivity measurement is measured on a continuous scale. So just looking at this, we can see that for the different sections of road that received paint 1, we have an average here of 27.75, 25, 27, and 20.25. One of our goals is to be able to see if there is a difference across the type of paint in terms of the reflectivity measurement. So this pushes us directly to what we talked about in Stat 5615, the one-way ANOVA. So before we get there, let's again characterize this design. The characteristics of the completely randomized design is that there's 1 treatment factor, but it can be a combined treatment factor. So right now we have the 1 treatment factor of the type of paint, but we could combine that again with other treatments and cross those as well. There's no blocking factor here, and we've talked a little bit about blocking so far, and then the next set of lessons we'll talk about implementing blocking, but with the completely randomized design, it's our most simple design. There's no blocking, so that means that there's only 1 set of randomizations. We randomly decide which of the sections of paint we apply which of the sections of road we randomly apply the paint to. Again, just some parameters or notation. We have T treatments. We have NI replications for treatment I, but here most of the time we're talking about balanced designs, so we could just call that N. And again, capital N is our total number of experimental units. So the target for right now is that balanced design, and you'll notice here that big N is your overall total number of observations. Little n is going to be that replication. So here's our statistical model. So in the background of this analysis is the CRD model, and I do think it's important to understand the model. And as we move throughout, I think it becomes more and more important to understand the model that relates to the design, because I think it helps with the analysis. So we'll start with this most simple case right now. We're going to have Yij, which is going to be the response. Okay, so that's just your reflectivity measurements. And the model allows you to have your response, and then with each part of that, you have kind of this mean that relates to it, and then this random error term. Okay, and in a second I have this kind of conceptual picture that will help you to understand those pieces. But this mean, we allow this to be different for each of our treatment factors. Okay, so that's important. And then the error term just says, hey, there's some background noise. We can't just explain everything. So we need this in here so it'll be a statistical model. If that wasn't there, then we would just have what's called a deterministic model. We make an assumption about this error term. We'll talk about that a little bit more in just a second. And we're going to assume that it's normally distributed, centered at 0. So that's how you read this. Your error term is normally distributed, centered at 0, and has a variance of sigma squared. This is called the means model. This is your statistical model. It's called the means model, but you can decompose that means model to actually use what's called the effects model. And I really like the effects model as we move throughout to more designs. So all we're doing is we're taking this mean here, and we're saying that there's a true overall mean for the experiment, and then there's these what are called treatment effects. So that's, again, let's talk about that a little bit more visually. Here's the what we call the effects model. And so here is your treatment effect, right? The effect due to treatment I. So this would be the effect due to a certain color of paint. And this is your random error term. And you assume that your errors are normally distributed. So let's look a little bit at this conceptual model picture. Here is mu, your overall mean. So there's a true mean, right? That's just if you took all the observations, you sum them up, divide by the total number of observations, that's your true mean. Now, again, this is for your conceptual model for the population. So we'll estimate these values later with data, but this is just the conceptual population model. Then for each of the 3 treatments that we have here, we have data. So that's what your X's are in each of these individual cases. You've got your X, right? That's your data. And so for that, you have a group mean, right? So that's that red dot here. If we're looking at it, then the distance between your observed data point and the overall mean, that's your alpha I. Okay, so so your alpha 1, or sorry, not your data point, the observed mean. This distance right here is your treatment effect. This one is the second treatment effect. This one is the third treatment effect. It doesn't matter if you use the simple model here, the means model, or you use the effects model. We're going to get the same analysis, but here you can see this is what we're looking for. And if there is a difference across the groups, then these alphas here are big. They're much different from 0, right? If they're all about the same and they're all really close to the mean, then it means that each group isn't very different, okay? The other thing is that we're making this assumption that it's normally distributed. So you can see here that I have the data. There's this normal distribution that's centered here for those error terms. This is telling you that the variability here, this could be a sigma squared if you wanted it to be, but again, it could just be the standard deviation. It tells you about the distribution of your data. So your data is normally distributed where your random error terms, which is your error term here, on average those are 0. Okay, so the error term for each individual group is your observation minus the overall mean of that group, right? That's what a residual error is. And with that, we look at the data. We can think that this data, although we don't know what it's going to be, right? The data has a normal distribution, meaning that we would expect more of the data to fall close to the mean, less of the data to be far away from the mean. And that's an assumption we make, and we'll talk more about that this semester. Okay, so again, I like this effects model. We'll talk about how this model expands as we implement blocking and other things like that. So we just talked a little bit about the random variability, right? We said that our error terms are random, which also makes our data random as well. So a random variable is any variable whose value changes from experiment to experiment. So if you think about it, and we're taking these reflectivity measurements, if we did the same experiment again, we wouldn't expect to get the exact same reflectivity measurements. So that the reflectivity, the response Y, is a random variable. Also, the error terms are random variable. The parameters of our model, though, the mu's and the alphas, those are not random. Those are fixed parameters from the population, and our goal is to be able to estimate those values. So once we start estimating those, though, then they become random, okay? And that's going to be something, if you took a more theoretical statistics class, you would talk a lot more about random variables, estimation, and things like that. But we need to have a little bit of that so that we are aware of what we're doing. So first of all, no big deal, right? Our data is random. If we did the experiment again, we wouldn't expect to get the same thing. And if the data is random, then the distance from our data to the overall mean, that distance has to be random as well. With that, with any random variable, you also can want to have an idea about what to expect with that random variable, meaning that if you were to run the experiment repeatedly over and over again, what would you expect on average for that random variable? So the expected mean value of a random variable, that's the expectation, is what you would expect if, again, you sampled repeatedly, and it's the average of all those sampled values. So it turns out that if you did the expected value of your response, if you did this over and over again, it would be the true mean of each group, okay, depending on the group, and the expected value of the error terms on average is 0, okay, and that actually played in right here too. This is the expected value of the epsilon ij. If you don't have a clear understanding of that at the moment, we'll do a whole lot more with that as we, not a whole lot more, but we'll do some more with that as we move throughout the course. And then the other thing that we'll talk about some is unbiased estimators. So an unbiased estimate is an estimate whose expectation equals the parameter being estimated. So if you've had any previous stat course, you may have looked at the expected value of the mean, right? Y bar, sorry, the expected value of the mean is equal to mu, the overall mean. That's an unbiased estimator. Y bar is an unbiased estimator of mu. So again, just if you've heard of unbiased estimators, you may have seen that before. So right now, I don't expect you to have a great understanding of even the idea of a random variable and expectation, but I'll show you where that becomes important as we move throughout. The other thing I want to spend some time doing is talking about the dot bar notation. And we did this in Stat 5615. I want to do it again here so that we're all on the same page. But again, if we have the dot bar notation, it leads us into some of our formulas for the sums of squares. So you got to understand what I mean by this dot bar notation. So to do that, I think I'm going to come here and give you a little bit more. So with the dot, if you see a dot, you sum, and if you see a bar, you take an average. Okay, so let's say that we have our data. So y1, let's say t is equal to 3 groups. So we have 3 groups, and n is equal to 3. So if you think about it, our first group, we have y11, y12, y13, right? So, and then our second group is y21, y22, y23. So this is yij, where I goes from 1 to 3, and j also goes from 1 to 3. This tells me my reps. This is n, this is t. Okay, and then we would have y3, which would be y31, y32, y33. Okay. So what you would say is if we wanted to take y1 dot bar, the dot means we're going to sum over that subscript. The bar means we're going to take an average. So what we're going to do is we're going to add all of these observations together because we're going to add the 1, the 2, and the 3. So this would be y11 plus y12 plus y13 all divided by 3. Okay? If we were going to do y2 dot bar, we would have y21 plus y22 plus y23. Right there, you just have y2 dot, right? But if we want to have a bar, we divide by 3. If you want to have y double dot bar, not triple, but just a y double dot bar, right? Then we can say that this equals, we could say it equals y1 dot bar plus y2 dot bar plus y3 dot bar over 3. Or you could have y double dot bar is equal to y11 plus y12 all the way up to what, y33, all of them, divided by the total number of observations we have, which is 9. So that gives you an idea. Again, if you see the dot, it means you're taking an average. If you see the bar, or sorry, the dot means a sum, the bar means an average. And again, these could be values. I'm just generically using the y11, but that could be like a 6, a 2, a 3, that kind of thing. So with that, we use this dot bar notation to actually show where we're making estimates. So remember I said that there are parameters in the population, but we also want to be able to estimate those values. So all of these are unbiased estimators, so it means that on average, this estimate that you see here will be the true value it's trying to estimate. So not surprising, again, we put hats and statistics on things that we try to estimate. The estimate of the overall grand mean is your y double dot bar, right? Just your overall average. The estimate of the treatment effect, okay? So the estimate of the, the ith treatment mean, right, is just going to be your yi dot bar. So that means you're just going to take your data that you have and you're going to average it. So if we look back at what we had before here, right, you'll see that this is your y2 dot bar. That's the same thing here, right? So each group mean, there's an average. The treatment effect, right, if you're doing your alpha I, that was that distance from your group mean to your overall mean, so it's just the distance from the group mean to the overall mean. You can see all of that here in the estimated model, and if you go back to what we did with the conceptual model, you'll see that there's a real link between the two. So if you're looking at it here, these bars here are your y1 dot bar, your y2 dot bar, your y3 dot bar. Those are just your group means. And then the distance from that mean from the group mean to the overall mean, that's going to be your alpha 2 hat. Okay. And then again, this is going to be like your y1 dot bar. Sorry. Okay. All right, so you get the idea of how that kind of estimated model works. If we're looking at our pain example, I just am showing you here a plot. I did this in JUMP, but the blue dots here are your data, and then you look at the means of each of the groups. Those are this is your y1 dot bar, your y2, your y3, and your y4 dot bar. And we could go in and put an overall mean onto this plot, and we could look at those differences. Okay? So we've got our model. Remember, our model is going to be yij is equal to mu plus alpha I plus epsilon ij. Okay, so if that's our model, we can actually write our hypotheses. And so, do the treatment means differ? Or do the treatment means differ by treatment? So one objective, one null hypothesis is that there's no differences across the groups. So this is using the means model versus that there are some differences. Okay. You can also say it in terms of the effects model. So if you say that all your means are the same, it's the same as saying that your effects are all equal to 0 versus at least some of them are different. Okay, so that's the way that you can write your hypotheses. This is the same as what we did with the one-way ANOVA. Okay, we didn't really talk about the one-way ANOVA in terms of these effects. We just said that all the means were the same versus at least one mean differs. The exact same thing. So with the ANOVA, the analysis of variance, again, our goal is to be able to look, do these group means look different from each other compared to the within group variability, right? The within group variability are your blue dots here. So in order to do that, we look at the sums of squares for the treatment, and it measures the variability due to the treatment effect. That's the group-to-group variability. So you'll notice that if you're looking at this looks at the distance of your alpha I hats, right? That's this value. It looks at those distances for the between group. The within group, or your error sums of squares, are just the within group variability. So if I was going back here, it would be the distance between each observation and that overall group mean, right? So you're trying to see if there's a signal for the noise. And then your total sums of squares is just each observation minus the overall mean, right? So this doesn't have anything in the total sums of squares to do with the model. But remember, we do have that additivity, so we know that our sums of squares total plus our sums of squares error also gives us our sums of squares treatment plus our sums of squares error gives us our total sums of squares. So now let's look at the test statistic. This test statistic is the F observed value. So you take your sums of squares for your treatment divided by the degrees of freedom for that over your sums of squares error divided by the degrees of freedom. Another way of saying this is it's the mean squares for the treatment divided by the mean squares for the error. Okay, so you can have that scenario. The degrees of freedom, again, give you an idea about the pieces of independent information you have to be able to get to that estimator. Okay, so this is the signal. The numerator here is the signal. This is the noise. Okay, it turns out that if you take this ratio, you have an F distribution, again with the degrees of freedom t minus 1 and n, capital N minus t. And we're going to do exactly like we've done with hypothesis testing before. We're going to reject the null hypothesis, conclude their treatment. The treatment has an effect if our F observed value is greater than the cutoff on the F distribution. However, I don't really rely on this bullet point because I don't use the F table. I instead look up the p-value that's related to this statement, and I'm going to reject my null hypothesis if my p-value is less than or equal to an alpha value, right? And the alpha is the significance level. So this should all be review, but we will do some examples in another part of this lesson so that you can brush up on the one-way ANOVA analysis. Here's the one-way ANOVA table. Okay, so again, we have our treatments, our error, and our total. These are the degrees of freedom, the sums of squares, the mean squares. Notice there's no mean square total, and then the F statistic. And when we're using software, we also will get a p-value from that. The notes here tell you some of the important things, but I just want to touch on those again so that you can make sure that you have that, because I expect you guys to understand the ANOVA table. Right, so I'm not going to write the whole table out again, but remember that the degrees of freedom for the treatment plus the degrees of freedom for the error, I'll put treatment here, equals the degrees of freedom total. So those are, you can sum those up. The sums of squares for the treatment plus the sums of squares for the error equals the total sums of squares. So they're both additive, right? If you have 2 out of 3, you can solve for the third. The other thing is that your mean square for the treatment is always the sums of squares for the treatment divided by the degrees of freedom for the treatment. All right. And then your mean square for the error is the sums of squares for the error divided by the degrees of freedom for the error. Okay, so the last part is your F statistic. I usually call it FOBS for the F observed from the data, and it's your mean square for the treatment divided by the mean square for the error. So again, I expect you, especially after Stat 5615, this should be a review, but you should be able to understand the ANOVA table and be able to fill in places in this ANOVA table if parts are left out. Okay. One thing here that's important is this F statistic is providing us statistical evidence in terms of our hypotheses, right? So again, if this F statistic is big enough, then we're going to reject the null and we're going to say, hey, at least one of these groups is different. I think that we have a treatment effect. That all relates to this kind of further insights page, and we'll come back to this as we move throughout the semester. But the reason that we talked some about expected values and random variables is this slide tells you why first of all, why your F statistic is your mean square for the treatment divided by the mean square for the error. And it also tells you why we look for big F-stats. So big F statistics mean that you have significance, okay? So just looking at it quickly to kind of talk about some of the important pieces, you'll notice that the mean square for the treatment, if you go back to look at that, it has all the YIJs in there, YI dot bars, so it's a random variable. So this mean square for the treatment is looking at the group-to-group variability. And on average, they're saying that this estimator has a portion of the background noise, and it also has a portion of the treatment effect. Okay? And then if you're looking at the expected value of just the background noise or the error, then it's an unbiased estimator of just your sigma square. Okay? So if you think about your hypothesis, our null hypothesis for ANOVA, let's go back. Sorry. So we'll do that here. Okay, so if you think about your null hypothesis, you have H naught, right? Which is alpha 1 equal to alpha 2 equal to alpha t equal to 0, right? All of your alphas are 0 versus at least one differs. So under the null hypothesis, under H naught, all of these sums of your alpha i's, all of that goes to 0. So you would agree with me that under the null, there's no difference across the groups, then the MST is approximately equal to the MSE. And if you're doing MST divided by MSE, then this is about 1. Okay? However, if one of these is different from 0, then this term comes back into play, right? That term comes back into play. And so we would have the sigma square epsilon, but then you have this term, and it has to be positive because we're squaring it, right? So this right here, this MST is going to be bigger than the MSE. So if you look at the ratio of MST to MSE, then this has to be bigger than 1. So that's why if your F statistics are around 1 or smaller, you're not going to see significance. If they're bigger than 1, then that's where you're going to see more of a signal compared to the noise. Now, how much bigger, that's where we relate it back to the p-values, the degrees of freedom, so it tells you how much bigger it has to be. But just to give you some intuition, that's why we're looking for big F statistics. So again, this kind of first lecture on the CRD, just to kind of summarize, make sure that you've reviewed, if from your Stat 5615, you have an idea about ANOVA, because that's what we're doing with a completely randomized design. And honestly, we're using the ANOVA analysis quite a bit as we move throughout the semester. But I've kind of introduced a couple new things here, talking about the statistical model and this idea of the treatment effect. I think that's an important thing to look at. That's your alpha i's. And then we gave you just a little bit of theory to get you grounded in what this ANOVA analysis is doing. So we'll continue on with the CRD and the kind of follow-up pieces of this lesson on CRD, going through some examples and talking about some follow-ups, but we'll talk much more about analysis at this point. So again, CRD, you have one treatment factor that you're randomly applying to your experimental units, no blocking, so it's our most simple design.